All right. Is that, yeah, are we good?
We can
Okay.
see it, Ben.
All right, yay. Okay, so I'm kind of jammed in the beginning of the strategic wood addition people and PBR people. At one point, Allison asked if someone could talk about like differences in planting rivers, larger streams versus smaller streams. And I don't know, I think we all kind of said, well, we don't really do much different other than species selection. We're kind of doing a lot of the same things other than, you know, if we have a great cornfield to buffer setting, then we can take advantage of a lot of natural regeneration stuff. But so anyway, didn't have a lot to say on that, but I said I wouldn't mind getting on my soapbox for a little bit to talk about prioritizing riparian buffer restoration on headwater streams versus larger streams and rivers, larger systems or higher order systems. And I started with this. This is one of my favorite false knees cartoon and that I follow, and just because it has a great forested buffer in the background, you know, branches overhanging stream. You got wood in the stream. You got some rocks. It's not just a bunch of silt. And you know, this is us, right? We're all, you know, out there trying to change the world and do our little thing in our little corner of the world. And what I guess I'm saying is, this is my chance to say, if I had to prioritize the funding in my program and state programs, that I would have a ranking for headwater streams that would prioritize funding for buffers there. Quick overview of, you know, to remind us all, which I had to remind myself of, this is sort of just one particular paradigm, talking about, you know, stream order and where we get the term first order, second order, etc. And this watershed basically down to, you know, maybe overlaps with the fourth order, but, you know, first to third anyway, is kind of what I'm lumping in today, calling headwaters. And this to me is where the rubber hits the road, where the action's at, where the fund's at, and where the greatest bang for the buck in water quality benefit comes from, particularly the practice of forested buffers, but as you'll hear later, strategic wood addition, process-based stuff, etc. All good. And I am going quickly. I have more slides than I should probably, but so this is just the same kind of diagram again, but, you know, highlighting some information here that, you know, basically 90% of stream miles in a watershed are, you know, 1 to 3 order streams, headwater streams, and that the quality of the watershed is most affected by these headwater streams. It kind of just makes common sense. This is a nice graphic from really cool UNH, or not UNH, New Hampshire habitat series they've done, and they have a whole thing on headwater streams. And I really like this sort of, this is another way to think about it for people. Of, if a river network is a circulatory system of a landscape, headwater streams are the small capillaries that fan out into veins, larger veins and arteries. So like basically, you know, what goes in, what gets in the capillaries is going to be, you know, in the larger streams, except we will get talking about some in-stream processing later. But that's why it's so important to have these buffers on, you know, these systems. And they just show a bunch of different kinds of headwater streams. Most of us think of the mountain streams, but we have a lot of these nice valley headwater streams, E-channel, slow winder through alder swamps, etc. Really neat, and a couple other examples here.
Hey, Ben.
And even yeah.
Sorry to interrupt. Is it possible for you to change your view so that we are seeing this slide and your next slide, and it's kind of hard.
Oh, how about that? Oh,
well, the preview's fun, but it's kind of hard to see what's on the current slide.
Oh, yeah.
You probably have presenter view on, which if you go into your
on
yeah, so right under monitor automatic, there's a toggle that says use presenter view. If you go back to the
Monitor on in PowerPoint or in
in PowerPoint.
Zoom? In PowerPoint.
Yeah.
Okay, where am I going?
So at the top bar, do you see where it says monitor and then there's that drop down that says automatic?
Oh God. Oh yeah.
So under there, use presenter view.
Oh, turn that off, right?
Yep. Now go back into your presentation and it should be all fixed.
All right, and we were here. Ugh.
Amazing.
Okay.
Thank you so much. Sorry to interrupt.
Hey, thanks. Okay. This is now my bailiwick. Okay, we did that. This is Nate. Great next image that Shayne has shared with me. Sneak preview from Shayne from a study and a tool funded by TNC and VLT. And I think he does as well. We both think it does a great job of showing a visual impact of how much of the headwaters, basically comprise how much the watershed is comprised of headwater streams. And they're in here, they're calling it, waters 1 and 2. But if you add in 3, you're looking at 85% of the watershed. It's a lot of area. It's basically the bulk of the watershed that is in this. Again, this is the Lamoille watershed. And so I just want to basically, ram it home that it's obvious that headwater streams largely determine the water quality and health of the higher order streams. This is also the Lamoille. Speaking of Lamoille, this is 15 years ago. I first worked on this farm. This is real quick, just talking about larger rivers. There's basically a natural levee here, and they had a 25-foot grass buffer. When I started doing CREP, it was already enrolled. And we've since, when they re-enrolled, we've enlarged this to a 50-foot forested buffer. And how to keep doing that. I know what I'm doing. There, yeah, 50-foot buffer. We're out here now, and it is all planted to a forested buffer. But again, that only goes so far. There's really no runoff off of this field, so it's not filtering runoff for the most part. You have a natural levee, and then it slopes down and then back up on the other side of the field. And we've got we're not going to shade this river with trees. So riparian buffer here is obviously not unimportant, but it's only so effective in protecting water quality. This is what happens after a flood, in corn ground, that you can see the chisel plow pan below and all that soil is gone. Same thing in another spot in the same field. So I'm not saying that, these forested buffers on these larger streams are not important. They have huge ecological value. They do trap a lot of sediment, in these, in the understory here. All these plants are evolved to come up through sediment. This is the wood nettle, and then you'll have a lot of ostrich fern. It's basically silver maple ostrich fern, some ash, and so all that's true. All these are great. I will still do buffers on rivers, but if I had my druthers, I'd be focusing on the headwaters. I love this graphic, basically saying, it lays it out pretty clearly: more effective buffers, less effective buffers. And again, they're the same practice, and basically the per acre, per square foot, much more important on smaller order or headwater streams than larger order streams. This is, to a degree, I wanted to mention this a little, sort of outside of riparian buffer world plug, of that in the Vermont state hazard mitigation plan here, 2018, headwaters are highlighted, conserving headwaters, inventorying headwaters for floodplain storage, conserving them, these areas, that speaks to how important they are. This is a quick example of a project we just did the pre-plant walkthrough on Monday on the Missisquoi in Sheldon. This is Missisquoi. We've got a river corridor easement on the river, 50-foot buffer. You know, which is fine, but this is where the action's at. These tribs coming in, this is a first order stream, and this is a second order stream once you get down here. This is where the fun's at. So this trib is on the left here. I believe actually Allaire is definitely planning or hoping to do some strategic wood addition with VYCC out here. She met with the farmer about that on Monday. But you know, all this will be planted, and then you know we will have it someday a corridor over this stream, so it will be very effective in improving and changing water quality in that stream. Same thing for this trib. I mean, you know, we're going to be widening out the, you know, they have an exclusion fence there. We're going to be pulling the buffer out here, getting this heavy use area further away. So both of these are exciting to me, impactful, more effective riparian buffer locations where the restored forest is going to make a big difference versus there. You know, the buffer down here on the river, we have the natural levee that comes over. You know, there's not runoff. You know, we're going to have trees eventually, but they're not going to shade the river. You know, we're not doing anything to really the water quality in the river itself, except, you know, when it comes out of the banks, it is dropping sediment out for sure. And then the buffer will be widened into the crop field there. So, you know, they're still important, but they're bang for buck, you know, acre per acre. They're not as important in improving water quality. And it's okay. Another current quick example. This is down on the headwaters of the Lemon Fair in Orwell, and this is a second order stream. At this point, the Lemon Fair is. This is a first order stream, which isn't even like identified on the BHT Carto, you know, which tells you like even intermittent streams when they should be based on watershed size. So I'm going to be showing you photos here first up above in the woods here where this stream comes down into a bunch of reed canary grass. This is Jaron Board. We're out here looking at stream size for it was maybe a culvert. We did a ford instead, which is better. But you know, here we are in the woods. You look at, you got leaves all through the brook, stones, you know, exposed. Soil here on the edge. We got ash, lots of ash. So you know, you have a brook. Then you get into the reed canary and it's gone. You know, like the grass ate my stream. We see this so many places, and it's just a shadow of its former self, right? Looking downstream, here's our ford crossing going to the Lemon Fair, same deal. You know, it's just crying out for alders and willows and a canopy cover. And then here's where it meets the Lemon Fair. It's all fenced out where we have wide buffers in this area. It's very wet. This is where cows formerly watered. We changed a 3-foot culvert to a 8-foot squash culvert to meet the new standards. Here we are in Troy Village, South Troy, basically. Again, Missisquoi, we have river corridor easements on this farm, this whole farm, all this, 50-foot buffers at a minimum on all this, some cases a little bit wider, and some outside bends. You know, that's all great. We have Beetle Brook here, like that's the most interesting part of that farm. All good, all very beneficial, but not as, to me, as important or interesting or overall, you know, again, moving the dime water quality wise as these first and second order and third order streams over here.
And Ben, you have about 2 more minutes, just FYI.
Oh my God. Okay. Yeah, this is that smaller trib. I've seen a brookie here. This is all gonna get planted. I guess this to me is a great spot for, we could do strategic wood addition here. Planting plan, we're going to be doing speckled alder, tamarack, shrub willow. This will transform these streams. This is Coburn Brook. You know, each channel should be alder swamp. I can't wait to see this transformed. You go upstream and we have one side touching, you know, spruce fir forest, large woody debris everywhere. This is a preface for you guys. All these benefits, again, that forested buffers offer, really, to me, are only fully realized in the headwater streams. You get nitrogen processing. Here's a stream in Cornwall. Up in the woods here, it flows 1.37 square miles down into the floodplain, and it's eaten by reed canary grass. This was a 12 to 15 foot bankful stream turned into 3 foot wide bankful wood stream, swallowed up by reed canary. Lost most of its function and value. Streams need carbon inputs and wood structure to be fully functional, and riparian buffers are a way to offer that. And again, I guess, you know, I'm saying the best way is focusing forested buffers on the headwater streams. They also offer in-stream nutrient transformations, particularly around nitrogen and denitrification, and you know that relies on the carbon fuel, again, which also fuels the entire food web. Yeah, this feels like you're trying to do a semester's worth of stuff in 5 minutes. Small streams, very vulnerable to impacts. This is up in the Rock River, trip to the Rock River. 15 years later, you know, this is a meaningful buffer on that stream. This is the most effective place to put these. It's the best way to take advantage of this practice. And, you know, if you dive down into this buffer, you have shade, you have leaves falling in, you got bits of wood eventually. It's never going to be a brookie stream, but it's transformed. Here's my favorite image. This is on the branch in Enosburg, and this was 15 years ago. And this is actually a couple of years. It's even better than this now. And here's my last bit. You know, by their very nature, headwater streams offer the greatest chance to benefit from a forested buffer restoration project. When you have the option, I know we don't always, you know, Fish and Wildlife has all these larger river parcels, you know, that we want to restore, obviously. But, you know, if you get the chance in your watershed group or planner or anybody, you know, conservation district, focus on the headwaters. Thank you.
I'm going to carry on with the headwater themes and go ahead and share my screen and show you all a little bit about the process-based restoration that we're talking about. I just want to kind of echo what Ben was mentioning, that, you know, headwater streams are really where the bang for buck is, because they act as a lot of the sediment suppliers. They're typically a higher gradient. There's a lot more of them. They cover a lot more acreage and square, you know, mileage and stream miles than our main stem rivers. And they've been neglected with, you know, converting land uses over the years, and they've been altered heavily because of the small size. It's actually easier to alter a small stream. So being able to restore some of these small streams and kind of capitalize on their disproportionate role in a watershed's health is kind of the main driver behind what we're going to talk about today. So what is low-tech process-based restoration? Well, it is just that. It's very simple. It's low cost, and we're adding structure to streams to mimic processes and functions that we deem beneficial to water quality as well as habitat. And when I say structural additions, you know, think of wood, think of beaver dams, think of natural materials that would fall into a stream or otherwise end up influencing a stream in an undisturbed forested setting. So structural diversity, complexity can be thought of as fine and large woody material. It can be thought of different sediment classes. It can be thought of organic matter like leaf litter and other detritus. You can enhance riffles and runs and pools and glides with structural additions. You can induce bed scour and you know, cascades. You can create point bars. You can create meanders. You can really modify a stream's character by adding structural additions. And we do that because we're trying to promote these functions that are good for the watershed, that are good for water quality. This means enhancing hyperetic exchange, like shallow groundwater, surface water interaction, recharging the local aquifer, the local groundwater, creating more wetland conditions in that hydrology, enhancing nitrogen retention and cycling and phosphorus retention, sorting sediments. That's important for aquatic organisms. It's important for maintaining that carbon source in a river. Rivers have metabolisms just like we do, and carbon's the main driver. And then also provides temperature buffering. It can help with cold water refugia. So it's these functions that really promote a functioning system, and we do it by bringing back the missing pieces. But we got to think about process-based restoration in the sense that streams change over time, they evolve. This graphic shows kind of a cyclical progression of a stream from stage 0, where we see, a single multi-threaded channel, single or multi-threaded channel that is essentially in equilibrium. It can change over time, and it evolves because of responses to changes in sediment, changes in precipitation and runoff, changes in floodplain connectivity, changes due to beaver activity or large wood inputs, successional changes in riparian vegetation. As you grow from a shrub wetland into a forested wetland, that influences how responsive the stream is because of the inherent characteristics of that riparian vegetation. And then streams also evolve because of natural or anthropogenic disturbances. So think of geological events, think of river encroachments and land use conversion. And so as these changes are influencing a stream, they go through these different stages, as I mentioned. We often call a stable stream a stage 0 or stage 1. And that could be, as I said, single or multi-threaded channels, but really it has floodplain connection. It's functioning in terms of supporting those beneficial processes, and it's solid, productive habitat. And then think of a disturbance happens, and we might send the stream into this evolutionary response where now all of a sudden it's eroding, it's incising, it's downcutting. We're seeing vertical erosion. Over time, we'll end up progressing through those stages into the widening and lateral erosion. And then eventually it reaches that maximum horizontal limits, and it starts to establish a new lower floodplain. It starts to aggrade and deposit sediment. And you can see that lower terraced floodplain showing up. How do I do that little, you had that little laser pointer spotlight.
Hit control.
Control?
Yeah, and then your mouse.
Oh, that wasn't it. Well, yeah, Shayne's doing it. So yeah, you have that little floodplain developing as it's grading and widening, and then eventually we hope to reach that new equilibrium, that quasi-equilibrium of a meandering or even sinuous single-threaded channel that's functioning with this floodplain. And so we try to expedite this evolutionary process by bringing back the structure that's missing. We have this progression of a classic, entrenched stream channel. It's got no floodplain connection. It doesn't have any structural function other than being essentially a ditch. We see these all across, our headwater systems. And so we can try to promote those functions and accelerate that evolution by bringing that structure back, by building small beaver dam mimicry structures and adding post-assisted log structures, which I'll describe more in a minute. But ultimately that provides, all those functions that we're missing, and it helps us to progress into that stable equilibrium state that, provides us with water quality benefits and habitat and clean water supplies and flood protection and flood storage and all of those other kind of co-benefits. So what does it look like? It looks like a bunch of boots on the ground, which is great. It looks like people trudging around in streams, building structures, adding wood, adding complexity. It doesn't necessarily look like heavy equipment. You could see, a large wood structure being put in the river. These have similar processes. The one on the left is intended to store sediment, to grade that channel, to raise the channel invert elevation, and to activate that sedgy wetland area on either side of the brook. But in the right picture, that big log structure is trying to force a meander in a river, in a big river, a fifth order river. And so they have the same kind of purposes, but they're done in different ways and on different systems. So up close, they look like some of the structures you might have built as a kid when you're messing around the creek. They are these leaky beaver dams. We're mimicking beaver structures. And you can see that there's quite a difference in head between, or there's quite a head between the upstream side and the downstream side. That might be 18 inches. And what that's doing is it's impounding that water. It's slowing the velocity down. It's allowing the water table to rise. It's allowing sediment to fall out of suspension. That increased residence time, the longer that water sits there, the more nutrient cycling that can be allowed to happen. It's in promoting floodplain and near stream connection. You know, and it's still, usually there's still fish passable structures. They can still find their way around, up or over these structures. And they can be made out of all sorts of natural materials, rock, you know, posts, logs, branches, stems, mud, sedge mats, all sorts of natural materials that are available within the vicinity. So this is one of the earliest projects I was involved in. This is on the Continental Divide in Montana. And you can see the old creek on the left. It used to be something you could step over. You know, it was 2 feet deep, 1.5 feet wide, and it functioned like a ditch. After a couple structures went in, we saw that channel width multiply by almost an order of magnitude. And it became this more wetlandy, floodplain functioning brook. And over 4 or 5 years, we were able to come back and maintain those structures and to add structures and infill structures. And all of a sudden, we're activating those floodplain terraces, and we're seeing different processes like sediment suspension. We actually, you know, this brook used to run dry every August, and it flows well into September now because of that natural groundwater storage that's being provided. Similar settings in farm fields. You know, this is a classic example of a ditched, channelized brook that went through a field or a pasture, and we're trying to bring that water table back. We're trying to restore that hydrology. We're trying to raise that channel invert. And this is, you know, on the panels on the left, that was just a matter of a week. The panels on the right, that was a matter of, you know, similar perspective or a different perspective on that same project as before. But you can see that that stream is a completely different system now. And now we're able to support tree plantings along the brook because they can tap into that water supply that went dry every summer. So a couple other examples of coming back to a project after the fact. You've done the initial install, and all of a sudden you come back the next spring and you see opportunities to continue enhancement. You can now activate low-lying areas that the brook is just dying to reach. So you can push water around the landscape. You can use rock check dams. You can use spreader logs to really manipulate flows across floodplains. And you can see as the brook comes out of that upper gradient or higher gradient landscape, it really fans out across this valley, which it used to do, but because of entrenchment and because of land use conversion, it no longer did that. But we're restoring that by just adding simple structural additions. And what we see is fine sediment. And so there was a comment in the chat about, well, isn't the phosphorus in the floodplains at the bottom of the systems? Like, yeah, that's where they're locked in. But those systems erode because of our flashy hydrograph coming down from the headwater streams. If we can slow that water down, if we can sink it, spread it, infiltrate it, we retain sediment from the headwaters, we keep it up there, and we buffer that peak in the hydrograph on the rivers on the main stems. You're really manipulating the whole system by working from the top down. You can also manipulate floodplains. You know, these are a lot of post-assisted log structures on a floodplain in Washington that really function as kind of a pinball machine. And you can imagine water flowing through this floodplain, hitting all these structures, creating all these micro eddies, all this kind of micro habitat. You know, what it's doing is it's allowing sediment to deposit on both sides of those structures in places. It's forcing wood that's naturally recruited into the stream to rack up against these structures and continually grow themselves larger and larger. And it provides structure in a floodplain that used to just be a field of reed canary grass. And we were able to reconnect it to the main channel and allow it to flood on occasion. And this sort of, you know, approach allows all this micro topography, which retains seed. So when we're talking about like Pete Emerson, Fritz, and Annalise's efforts on direct seeding talk about opportunities to capture that cottonwood and that willow fluff that it needs to hit a germination substrate immediately. This is providing that germination substrate. And then another simple iteration are these log and earth beaver dams. These are 1 foot high berms that we build from native soils on site. We sink a footer log on 50 feet each side of the overflow. And all of a sudden we're creating acres of wetland habitat with really low tech. This is done with a mini excavator in 2 days. And you can really tap into those headwater systems and activate those low-lying wetland complex areas that might have actually been former beaver ponds in days of yore. So a couple of other structures that you can apply, they don't necessarily have to live in perennial streams. These are ephemeral gullies that really only flush during rain on snow events, but when they do flush, they're putting out tons of sediment. So we build these gully plugs, these gully check dams out of logs, out of post-assisted log structures. And what that does is it allows sediment to be retained in the gully. It provides resiliency, it accesses those lower floodplains, and it really stabilizes that creek from continuing to downcut and erode. Note that these are being built with work crews. These are not volunteer-driven projects. This is a lot of manual labor, and you can't rely on folks who, are only there for an hour and a half on a Saturday, because it takes some time and some expertise to build these. So when I'm driving around the Northeast Kingdom and I'm looking for project opportunities, this is kind of what I'm eyeing. I'm screening for projects where there are, culverts or streams that come out of the forest and they span across, developed lands, and they might be channelized. They might have a head cut. They might have no floodplain connection. They might be an urbanized setting that looks more like a stormwater ditch. They could be a little culvert that dumps out into a field that could support a wetland, but no longer does because of conversion. So I'm looking for all these characteristics that are suitable for process-based restoration and water quality improvement. And really what you got to capitalize on are these low gradient systems. As I mentioned, brooks coming off the hillside, crossing the road, approaching the floodplain, really capitalize on that low gradient, most heavily impacted reaches where you can have 7 or 8 ditches that could be suitable for process-based restoration to keep sediment, to keep water on the landscape, and to restore those processes and functions. So there's some do's and don'ts. Work with experts to know how to site these and select the methods that are appropriate. Talk to your fish biologist, talk to your river scientist, your floodplain manager. You got to get approval for that. Focus on those headwater streams, as Ben was mentioning. Design and build with redundancy. You see in those photos, we don't just build 1 structure or 2 structures. We're building a lot because we don't want a structure to fail and the whole project to unzipper. So you got to build with redundancy. Infill structures over the years. Plan on 3 to 5 years of maintenance and monitoring and adaptive management. Use those local materials and use experienced work crews. This is not a set it and forget it project. And you need to be, building them tough. You need to be maintaining them regularly, and you need to be operating them so that they continue to function and provide those services before this, while the stream is essentially repairing itself and getting itself to a positive ecological trajectory. Here's some resources for those who are curious. There's a great book about this called Let the Water Do the Work by Bill Zedike out of the Southwest. I'd recommend that read for anyone who is interested in learning more, and feel free to reach out if you'd like to chat.
Great, thank you. Thank you, Patrick, and thank you, Ben. That was really great, and it was a really excellent lead up to what we're going to talk about. And I was kind of watching the chat. There was some wonderful conversation going on there, and I think that sharing our case study from Colchester is going to just show one example. It's one very small headwater stream, kind of a pilot for some of this work in Vermont, and hopefully that will just show one way that this can be applied in Vermont. So let me share my screen. So this is we're going to talk about this project that Shayne and I, along with Bob Himes and University of Vermont collaborators, worked on in the past year. This is on Crooked Creek, which is a first order headwater stream in Colchester. It is about a mile from Lake Champlain. It just flows into one other small creek before that water reaches the lake. This site, let's see, is on a farm. It's right along Route 7. So this road that you see on the left is Route 7. The drainage that we worked in is this area that's really just full of a lot of white pines. The pond that you see in the foreground is a small farm pond that was created by building an earthen dam on Crooked Creek that you can see in sort of a brown goldenrod covered dam there. This was in October, maybe November last year. And Vermont Land Trust has site control on this land, and we are implementing a kind of a multifaceted restoration project in this drainage. You can see that it's actively farmed by a couple different farmers on both sides. And so our work is really working in the context of that active farm work happening around it, having the road, busy state highway passing right by, a lot of impact over the years in terms of, like, you can see sort of areas of rock that have been placed here to shore up this farm field right along Route 7. There's more over here. A lot of this slope in the foreground is on the left is sort of artificially steep because of fill that has been put in. Obviously the dam is there. So our work is really a combination, part of a multifaceted approach. So I'll just say that we are working to remove the dam later this year in the fall. So this is an image from 1962 that shows the dam maybe about 10 years. I don't know the exact date it was put in, but it was late 40s, early 50s when the dam was put in. And you can see that the Crooked Creek drainage, so that the blue line that's there was completely, almost completely denuded of trees in 1962. So it's really interesting just to see how, you see those white pines, which are really commonly, the first early successional trees that come back. This was cow pasture. Cows were all in and out of the creek. They were wandering around down there. There was a lot of erosion. There's at least 10 gullies that you can sort of see from the north to the south. There's a big one up here, and they're not as incised in this photo as they are today because of the impact of the farming over time. So it's a place that really could use a lot of restoration work. It's exactly the kind of place that Patrick was just talking about, these kind of like old pastures, places that have really been kind of overused. And, as Ben said at the beginning, these small streams were easy to manipulate. They're easy to dam. They're easy to have cows in and out of. And so coming back from that is, it's a fun challenge because it's also not an overwhelming challenge. The stream and the whole drainage there are small enough that these kind of process-based, very small scale in our case, which have been done by volunteers, these approaches really work well. Shift it to Shayne. Shayne, just let me know when you want me to advance those slides.
Thanks, Allaire. Hi, everybody. So I'm going to speak a little bit about the ecological need for restoration, but before I do that, or at least on Crooked Creek, before I do that, I just want to explain that a lot of what we're talking about with process-based restoration, particularly on this project, is in the context of lower slope rivers and broad alluvial valleys, where we really do have an opportunity to push the river around and reconnect it to its floodplain, as opposed to steeper rivers and narrower valleys that are controlled by bedrock. And also that, the distinction between those two is somewhat fuzzy as they, as they merge together. So anyway, just wanted to set that context. So why do we need to restore this reach of Crooked Creek that is in a forested and apparently undisturbed setting? And you all, I think, know the answer. You just saw the previous slide, and the setting didn't always look like this. And the creek has been through some tough times, and as a result is really in a very deeply incised condition. I mean, this is a tiny creek, and those banks are like 3.5 feet tall. So it's very deeply incised. You could advance the slide, Allaire. So there is an impact of incised rivers, a really significant impact. So the DEC Rivers Program has found that 75% of 5,000 assessed river miles across the state are in an incised condition, lacking floodplain connectivity. And incised rivers convey flows at really high velocities with really high erosive power. They scour away habitat, threaten adjacent human investments, flush nutrients downstream, and certainly increase flood stages downstream. Incised rivers don't hold up the local water table or spill flows onto the adjacent landscape with the frequency required to feed and sustain those adjacent floodplain wetlands. So if we're going to improve Vermont's freshwater ecosystem resiliency for the purposes of, water quality, riverscape habitat, flood resiliency of human communities, we really have to tackle this process of river incision and restore our rivers' connectivity to their floodplains. You can advance the slide, Allaire. So the process-based restoration approach that we take at Crooked Creek and elsewhere is really influenced by the latest scientific understanding of river processes and how rivers change over time when they're disturbed. And Patrick ran over some of this, so I'll try to be really brief here. But just a different way to think about it. Our older, understanding of river change or evolution envisioned that the pre-disturbance river was most often, if not, well, most often having a single thread channel shaped primarily by forces of geology and hydrology. And once those rivers incised, they weren't envisioned to really ever return to their previous elevation or a grade, as Patrick showed, and reconnect to their former floodplain or create new floodplain at an elevation that was close to the former floodplain. So this is what our template was when we designed and restored rivers. And Allaire, if you can advance the slide. More recent research strongly suggests that the pre-disturbance rivers most often had multi-thread channels that were shaped as much by biological factors, including beaver activity, in-stream large wood, living vegetation that maintain complex and well-connected river floodplain systems. And that when those systems did incise, that wasn't the end of the story, but rather that they could come full circle. They could aggrade and reconnect with their former floodplains, or floodplains that were at least as close in elevation to the former floodplains. So process-based restoration really seeks to restore the biostructural elements to advance the channel evolution process of our incised streams, to restore them to that original or pre-disturbed condition. Okay, we can advance the slide there. So beyond being aligned with current science, process-based restoration has some other really important benefits or traits. One, it's ideal for working in these headwater rivers that we have talked about as being so important. It's much less expensive than projects that are designed with a lot of modeling and engineering. Not that there isn't going to be a place for those types of projects, there always will be, but they are expensive and they're constructed with heavy equipment. And because PBR projects are not designed with all the modeling and they don't require heavy equipment, they are much less expensive to implement. So we can really scale up this work with the budget constraints that we have. And finally, is equally as important, I agree with Patrick, you can't put a bunch of volunteers out on a site and expect a whole lot of work to get done. You always need to back that up with the pros, but we can engage volunteers in this work and get them excited about river restoration. And we can, increase their understanding and awareness and turn them into advocates for freshwater conservation work. I think it's super important. Okay, we can advance that, Claire. So we have some basic design principles that we followed and on the Crooked Creek project. And I think Patrick hit on a few of these, so I'll be really quick. Structure forces complexity. So we want to add a bunch of structure and force complexity. Inefficient conveyance of water is healthy. Patrick showed that beautifully. It's okay to be messy. We don't need neat structures. We can just throw a bunch of wood in the stream. That is my favorite principle. There is strength in numbers, as Patrick said. We don't want to just build a few structures and watch the thing unzip. We use natural and local building materials, and ideally, as we did at this project, those are harvested invasives such as buckthorn. And then these systems, the self-sustaining systems are really what we're after. We need growing riparian plant communities and beaver to continue to feed these rivers over time. We want to let the systems do the work, add the structure and watch the water reshape the channel. We don't need heavy equipment to do a lot of excavation. And then in this project, in the context of this particular project, we had to consider previous gully stabilization work that had been done and make sure that we weren't unraveling that work. And also with this project, we wanted to align this work with that dam removal project that Allaire mentioned. So if we can put a bunch of structure downstream of the dam removal, when that dam is pulled and some sediment is washed downstream out of the impoundment, which always happens with dam removal projects, you know, can we trap that sediment and regrade and build up that channel bed for the purposes of restoring that channel? And we can advance the slide, and that's back to you, Allaire.
Thanks, Shayne. Just wanting to quickly show the design for the dam removal that's going to be happening at Crooked Creek. And so you can see the this orange outlined sort of banana shaped thing that's going to be the new stream channel where the dam was. And then the black line that continues to the northeast is Crooked Creek. And so in our whole process here, we have been coordinating with Evan Fitzgerald and Rodrigue Spinette from Fitzgerald Environmental, who are designing and will be overseeing the dam removal later this year. They've been really important partners to just like make sure that they know about this in-stream wood addition. It's really been an interesting kind of back and forth. There's been a lot of learning on both sides, whereas we think about how the dam removal will be impacting the wood addition. And so like Shayne said, we wanted to make sure that we built the wood structures in advance of the dam removal, knowing that that sediment that would be mobilized during the removal, some of it would be trapped by the structures, and we're hoping that will happen to regrade the channel. So I just wanted to share this because I just got this the other day and I'm kind of excited about it. We're going to be hoping to get this former pond site back into that anastomosane stream set up with some little wetland pools, you know, wood added in there as well. So I wanted to take a little bit of time here just to talk about some logistics. And I think it was Ron who asked in the chat about, have these projects been permitted in Vermont? One really important part of the collaboration that Shayne and I have on the Crooked Creek project, but also a couple other wood addition projects we've done, is to really try to develop, and I intend this pun to streamline the permitting process for this type of work, because it is so simple. Like folks have said, it's like you're a kid again, you're sticking wood in a stream, you're just like using material that you find. We want to make this accessible to people. It is by its very nature, but it does require a permit from the Army Corps of Engineers for a stream this small. When you get into bigger streams, you need to work with stream alt processes as well. But this stream is below the size threshold for that. So I just want to give a little bit of like explanation of kind of how we've gone about doing that. I think with any process, there is a tendency to try to make it really complicated and really good and take time and be really beautiful. And Shayne and I were very intentional, like, let's just do the simplest maps that we can to get this permitted through the Army Corps. And Mike Adams and Angela Rapella have been great partners in terms of talking this through with us and helping us figure out the approach. So these next three slides are just the images that I submitted with our Army Corps application. So we needed to do a site map, just use publicly available LiDAR and contours for that. Ordinary high water was just estimated. We estimated that the stream was, I think, 6 feet across. And so I just buffered, the streamline for that. Did not need to do complicated work or analysis to create that. And then for these, the longitudinal profile and the cross-section profile are required for the Army Corps application. And so we worked to figure out a process to do this. It is super simple. I think people with more GIS skills than me would be able to even automate this more. But what I did was I just took the streamline from the Vermont Hydro data set, the 1 foot LiDAR generated contours, like you saw. Well, I don't think actually the previous map, I think, was just the 20-foot contours, but I looked at the 1 foot contours and just figured out the slope of the stream for the reach that we were doing, which is about 1,400 feet below the dam. So I just made an Excel table, brought that into PowerPoint, added a bunch of really rudimentary graphics here, some posts and some pieces of wood, and sort of, it's really basic. And I think that's the point. We don't want to make this more complicated than it needs to be. And this has been sufficient. So this is the third project that we've submitted and received a permit for. It's been really easy. And yeah, I can give more insight if people need it, but I think that probably most people can just look at this and maybe just go do it themselves. The cross section is the same thing. I looked at those 1 foot contours from LiDAR. That's all freely available. You can download your project area shape files from VCGI and overlay that in GIS. And I guess you do need GIS, but there's different ways that you can access that program as well. So I looked at those 1 foot contours, looked in this case, I just took one kind of cross section across the creek and created that channel shape. Again, stuck some really basic shapes in here. I think that I did this on a PowerPoint slide, some labels, and we're done. So it's meant to look really basic. So I think that's a plus, and something that maybe it'll just make it an easier, low barrier to entry for folks. And Shayne, I think you're going to talk a little bit about design process.
All right, thanks, Allaire. Yeah, so this is going to be a really general rundown on the design process, but it is intended to be pretty simple. But anyway, here's what we did. So, we began with river and ecological science expertise that both Allaire and myself have. We thoroughly read the Lowtech PBR design manual, and we watched a lot of the online training videos that they have. And just a shout out to that whole resource. It's fantastic. Just search for Utah State River Restoration Consortium, LTPBR, and you'll find it. We also engaged Bob Hyams of Riverscapes Ecology, and Bob is a trained LTPBR professional. So we had his expertise as well. And it's really important, I think, we started a couple of years ago with some really, really tiny projects before we stepped up to the size of Crooked Creek, and that was really helpful. So I think that was an important part of our process. So when we got to Crooked Creek, we set our overall planning objectives. We assessed the existing geomorphic condition of the river segments within the project reach, focusing largely on the stage of evolution of each of the segments. We identified the goals for each segment, which might be to erode the banks, to widen the incision trench, or maybe to impound flow, to inundate the adjacent floodplain, all depending on the existing channel conditions. We designed complexes of structures. So one of the big things in PBR is you focus on complexes of structures rather than just individual structures to achieve the goals of each segment. And again, we followed the guidelines of the LTPBR manual. We use structure typicals. They have great typicals, all intended to help us all do this. They encourage us to take those typicals and use them for permitting and our own design process. So we use their information to design our individual structures. And of course, we kept the guiding principles in mind throughout the entire process. I think that's really important. So that's really it. On the just a general overview. So Larry, you can advance the slide if you would. So this is kind of like, what the design or the construction process looks like. Looks like fun, right? Like we would all love to do this rather than sitting at our desk pushing the most around. So, with a crew of about 14 people, we built, I think, about 26 structures on the 1,400 feet of the creek. I think we did that in about 4 hours. So, this can be really quick and easy, and people love to engage with it. So that's the construction process snapshot. You can advance the slide, Allaire. So we're going to move into results now. I'm going to tackle this first slide of results, and then Allaire is going to take it over after this. So, what we're looking at here on the left is pre-project photo. And I just hope this conveys the minimal amount of water, like the very small amount of water that was typically in this creek before the project. We have sort of a sandy alluvial substrate, and it's a very flashy system. And I remember when we were trying to encourage Beverly Wemple to engage her students to come out and work on the site with us. She got out to the site the first time, and she kind of smirked and said, "This is it." and I felt like, yeah, right. But look, after we put in this wood structure and we increase the residency time in the image on the right, we're holding water. Now, to be fully transparent, this photo was after a pretty significant rain event, but it was 4 days after a pretty significant rain event. And the creek is still holding water. And I don't know if you can tell, but that's a little inset floodplain on River Right. And the flow is almost accessing that floodplain. And we haven't gone through that process of capturing sediment yet and regrading the channel. when we took this picture, there were frogs jumping in and out of the brook. There were insects moving around. It was really great. And I know these look like check dams. And yes, you can say, yeah, you're just building check dams to hold water. That is true. But the intent is for this stuff to fail and to drive river change, to continue to advance that channel evolution process. So that's really what we're after. And just to the point, this is supposed to be a self-sustaining system in the end. So we're not done yet. We need to come back. We'll need to maintain these structures. We'll need to add new structures, like Patrick said. This isn't a set it and forget it sort of approach. And of course, we absolutely need riparian vegetation to continue to feed this river with woody structure over time. So with that, I'll pass it over to Allaire and she'll wrap things up.
Great. So I think this is that same area that Shayne was just showing, that same reach, an aerial photo that was taken 3 weeks after the structures were built. This is similar time after that fall rainstorm, several days after the rainstorm. So just pointing out a couple things. These red circles, the one closest to the top is one of the Beaver Dam analogs, and you can see the real difference in the water that's retained behind it and spreading out to the right and to the left into the floodplain. As compared to the stream channel down below, which is sort of that incised narrow channel. Moving clockwise, there's a pile of material that's left over. We'll use that in future years. This is all buckthorn that was treated by Bob Himes in this same valley. So Bob treated the buckthorn, he cut it, treated it with herbicide, and then left the stems in piles. And he did that the year before. So this was a great source of material that we really love to use. Just next one upstream. So the stream is flowing kind of up here, flowing north, is a post-assisted log structure that's anchored on river right. So that is a structure that you can see this kind of accumulation of logs and sticks, and the water is flowing slightly around it. And then the last photo was a hay bale. So this is a farm that produces a lot of hay. Gene Button, who's a longtime farmer there, had actually donated 10 bales of hay to us. And he was really, he's a fourth generation farmer. And I believe he's in his 80s. And he was really interested and excited in this work. Had a lot of questions, and it was really great to engage with him. He came down and donated this material to us. And so we included that. We also used hay to sort of stack up behind the Beaver Dam analogs. Just a close-up of a post-assisted log structure on river left. And you can see that this is having the impact that the water, the flow is really driving to the right side. So what's happening here is that the incision trench in the stream is widening. So the river can rebuild floodplain at a lower elevation and advance that channel evolution process that we've been learning about. And then here's a close-up of a Beaver Dam analog. And you can see in the lower central part of the image, the water that is really extending out onto the floodplain. I don't know if you can see my cursor, but it's coming out into the flat floodplain where before it would have just been continuing down through that narrow incised trench. You can see the hay that we used here. We also had willow stems that we wove in between the buckthorn uprights. Finally, I just wanted to share this kind of before and after. This was LiDAR that we commissioned Fluid State Consulting to take for this project, just because it's a demonstration project. We won't be doing this for every project, but it's just a really great resource. And you can really see, I think, even these are 3 weeks apart before and after the construction, that the picture on the left is, it's just a lot more of a deep line. You can see the hillshade kind of showing you the channel for Crooked Creek. And on the right, there's places like the uppermost BDA that you can see. If you see my cursor, you can see that there's some change. You don't see as much of that deep shaded line. And so already this is having an impact. This was, I think that this was flown after one of those rainstorms. And so the water itself contributed to the image, the hillshade here. But I think we're already starting to see this impact of what the water's doing, and then ultimately how sediment will be aggregated here. And finally, just wanted to thank all of our partners. So Riverscape Ecology, Bob Himes has been just a critical partner here. Beverly Wemple and her Hydrology of Forested Landscapes class provided the labor for both building the structures and also surveying some cross sections that we'll use for monitoring. Fluid State Consulting and Fitzgerald Environmental have also been great partners. So please reach out to Shayne or I if you have any questions about this. We're happy to chat and to see more of this happen on the ground. Thanks, everyone.
Okay. All right. Yeah, let me know if you can't see my presentation. But I'm going to talk about what I consider, I've come to realize is actually just a different flavor of low-tech process-based restoration. You know, that terminology, the low-tech process-based restoration, really kind of developed out west, where they've got different types of streams, different kind of problems they're working with than we do here. But their techniques certainly apply, as we got to see in our last two presentations, which were great. Strategic wood addition is a different tool, fits in a little bit different situation. You may gather as I go through this that we're working on a little bit bigger stream, and we're working on streams that have a lot of trees in the riparian zone that we can utilize to add wood to streams while still maintaining all the functions of the riparian forest. But what I want to do is just kind of give you an introduction to strategic wood addition. And everything I'm going to talk about and a lot more you can find in the Vermont Strategic Wood Addition Handbook. If you Google search that, you'll find it. It's on our website, Vermont Fish and Wildlife website. If you have any trouble, just reach out to me and I can get a copy to you. So what I want to cover is, what is strategic wood addition, talk about why we would add wood to streams, which, we've talked a lot about that, but I'll give you a little bit more on that. And then why we would use strategic wood addition versus some other methods. All right, so to explain what strategic wood addition, I'll just break it out into the 3 words and I'll go through it in reverse. So it's addition because we're adding something. And in this case, it's wood. And for the most part, that is in the form of trees that are growing on the stream bank or close by. That, that's a very cost-effective source of material to add. These kind of projects could be done by bringing wood in from some other place. Usually we're using a chainsaw to drop these into the stream. And it's strategic because it's not just a random process. We put a lot of thought and planning beforehand and deciding where we're going to do this work, selecting the stream reaches, because there's only certain places where this is really going to work or where it's really going to make sense. And you can get more details on that from the handbook. It's also strategic while we're out there because we put a lot of thought into which trees we are going to use and how we're going to get them down, how we're going to get them secured if we need to. And then there's monitoring that goes on afterwards. So there's a lot of thought planning work that goes through the entire process. So that's why we use the term strategic. And I think about it as coming in 2 categories. On small streams, and to, if you want to know what I mean by small streams, the details you can find in the handbook. But basically what it means when I say small stream, it means that the trees are large relative to the channel. And when you have that kind of a situation, you can drop a tree into the stream and the stream isn't going to be able to move it very easily, or maybe not at all. So that's relatively easy. You drop a tree in the stream, it's going to stay and it's going to function. We use what we call chop and grip on a little bit larger streams where the trees aren't so big relative to the channel. So this is a type of stream where you could drop that tree in, but the stream is big enough and powerful enough that it could move it a distance. And so you take some additional actions to secure that wood in place. And it's called chop and grip because we're using a grip hoist, and you can see the grip hoist here. It's like a big come along. We can drop trees with the chainsaw and then reposition them, locking them in place. There's several methods that we use. Again, you can see those in the handbook. Or we can bring entire trees in, roots and all, using the grip hoist. And yeah, so again, that's a method on a little bit larger stream. Helps to get that wood more secure. So why would we add wood to streams? A quick answer is because a lot of our streams look like this. And to a lot of us, that probably looks just fine. And that's because we are generations removed from knowing what our rivers really originally looked like. A lot of our streams look like this. This is a really good transport channel. This is good at transporting sediment, transporting wood, transporting leaves, organic material. And that's because a lot of our streams, this one included, were used to drive logs in the past. And when you want to float logs from the mountains down to the mills, you want to get all the boulders out of the way. You want to get things straightened. You want to get any wood that's in the stream out of there. And that's still what we have a lot of today. We have rivers that are really good at moving wood and sediment and all that stuff. Whereas because those big boulders and that wood has been taken out, and those were important features for stream function and fish habitat. And on top of it, we have cut our forests right down to the rivers multiple times. And so we don't have big old growth trees that are just naturally falling in on their own and being stable and performing all those functions that we want wood to perform in our streams. And so really one of the main motivations we got into strategic wood addition was, we wanted to improve habitat, but we also wanted to communicate the value of wood in streams. We want wood in streams so much that we are willing to go out there and put it in there ourselves to highlight the fact that what we really want to do is we want to restore and protect our riparian forests, because we want to have big old trees that are going to fall in and they're going to be stable and they're going to create natural wood jams like this one here. And we want people to know that when wood falls into the stream, we want you to leave it there. As I said, we're a couple generations removed from seeing rivers that had the amount of wood in them that they would have had in the past. And so now when trees fall in, it's not uncommon to hear from people that think, we need to do something about that. That's not right. That's not natural. We need to get that wood out. Even anglers sometimes think that wood isn't good for fish. So we're trying to change that culture around wood. And one way to do it is by going out and doing it ourselves. Also, the reason this fits into process-based restoration is because adding the wood is part of restoring the natural process. We can't go out there forever and just keep adding wood, but we're trying to jumpstart it by getting some wood in there that's going to catch natural wood. And so none of this would have happened without partnerships. Trout Unlimited really is the one that I can really thank for getting us started on this. We were joined by U.S. Fish and Wildlife Service and Weyerhaeuser working on their lands in northeastern Vermont. And just to go through the process of how we got there, first, we wanted to do good things especially for brook trout. And so the first thing we needed to figure out was what can we do? And so we needed to figure out what factors were most limiting for brook trout populations. And we focused on northeastern Vermont, and we did a study. It took us 3 years. And we found that the most important limiting factor was water temperature, which wasn't surprising because we know that trout need cold water. But the other thing we found was that the amount of large woody material in the streams was the second most important factor. It also gave us a target. So we knew if we had at least 80 pieces of large wood per acre of stream, we should see an increase in brook trout abundance if the water temperatures are suitable. So armed with that information, we were able to go out and assess the habitat that was out there. We prioritized where we were going to do this work and add wood. We started adding wood in 2012. We've done a little bit every year since. And then we've been evaluating our work. And so as a means of talking about the functions that wood performs, I'm just going to talk about the functions that our structures perform because we're just trying to recreate natural wood jams. This here, we have of the wood structures that we've put in on our little bit larger streams where we've needed to use the grip hoist, we have tagged those individual sites so that we can go back and monitor them because we want to know how long they're going to stay in function. We don't do that so much on the smaller streams because we know that they are gonna remain and function, but we really want to keep a closer eye on the bigger ones. So we have 620 structures that we've been able to follow for multiple seasons. And most of them are still in the place where we put them, and they're still performing at least one function. And I just want to go through some of these and just highlight them. So one of the most common functions that they perform, and maybe one of the most important, is they're retaining organic material. As I said, a lot of our channels are really good at transporting things, including organic material. This is a problem for two main reasons. One is that organic material is the base of the food web. Those leaves decompose, they become food for insects, which are then food for fish. So we want that food to stay up there and increase the productivity of our stream. At the same time, by keeping that organic material up in these headwater streams, we're keeping that material from getting downstream. And those leaves, even though, you know, it's not manure, but it still has nutrients in it. And so we're keeping that stuff where it can be processed upstream rather than it coming downstream where we really don't want it. Also, our structures are, and natural wood does, retain sediment. Got an aerial photo there on the left from a drone looking down at a structure that created a pool, and you can see on the upstream side, which is on the right, the substrate looks a little lighter. That's because there's a lot of fine sediment that has settled. Fine sediment that we're keeping up in the headwaters that is not going to make it downstream, where we really don't want that sediment. We're also narrowing the channel and scouring some deeper pools. As you can see on the right, this structure is just on one side of the stream. But you can see a gravel bar forming right down here on the downstream side, which is narrowing our channel during summer low flows, which is decreasing the surface area. So there's less, less surface area to be exposed to the sun. And also it's creating a deeper pool there, which is important for fish habitat. We're also forming some pools, which is important for fish, especially brook trout, and especially in the winter. And then increasing floodplain access. So in some cases, we're able to get enough wood in there where, just like in Shayne and Allaire's presentation, where they were able to kind of get, start to get that water spilling out into the floodplain, we're able to do that by adding wood in some of these larger streams. And that gives us the benefit of allowing that water to kind of dissipate its energy out in the forest rather than coming rushing downstream where everybody lives and causing problems, also dropping sediment out in the forest. Yeah, so this is a benefit that hopefully it benefits more than just the habitat, it benefits people as well by preventing some of that flashiness of flooding. And, as I showed there, we had those 620 structures that have been tagged that we've been following multiple years. Some of them they aren't functioning where we put them. It doesn't mean they're not functioning, it just means they're somewhere else. And that wood has moved, which is a natural process. Wood is going to move. You just need to account for that when you're designing these, knowing it does move where it's going to settle. But it's it often settles on either another structure downstream or on a boulder or on an outside bend, and it's still performing functions where it is. It's not a loss to the system. All right, so the big question for us, of course, we really got into this for brook trout purposes. So I just want to talk about a study that we did to determine how this, did this really benefit brook trout. We used stream electrofishing to sample brook trout populations in the East Branch Nalhegan River and two of its tributaries for 2 years before we added wood. So we had 2 years of pre-treatment data. Then we added wood and we sampled for 4 years after. So we added wood to everything but the control sites. And as you can see, the control sites were intermixed with the treatment sites. We had 9 pairs of control and treatment sites in this study. And what I'm showing here on this graph is brook trout biomass. Biomass includes the number and the size of fish. And, both of them increased. So the size and the number of fish increased. At our treatment sites, as we expected, one of the questions that people had early on was, how do you know you're not just concentrating fish in the areas of good habitat, so pulling them out of the control sites into the treatment? Seems like that probably happened the first year in 2014, which isn't surprising because the population doesn't have time to respond that quickly. Need time to reproduce, make more young brook trout and occupy those habitats. But as you can see there, by the end of our study there, the control sites had actually rebounded, and actually there are more brook trout in our control sites than there were before we added wood, even though we didn't add wood to the control sites. And that kind of makes sense because of all the benefits I mentioned earlier about wood. We expect those to spill over into the control sites because we're going to have more juveniles produced in the treatment sites, maybe that are going to spill over. We're going to have more food in the system. So we're not just concentrating fish. We actually have more fish out there as a result of this work. Then just finally, why would we use strategic wood addition to add wood versus some other methods? And, there's definitely some, certain places where this is effective. Some of those other low-tech process-based restoration methods are going to be better in some situations. And in some situations, using the big yellow machines is going to be the best way to but compared to some, using machines, this is a lower impact method where you're able to use it. We don't have to drive a machine in the stream or over the stream banks. And it's been proven effective. We've really closely monitored this and proven that when it's done in the right way, in the right places, we're going to see benefits from it. Just put this up here to just thank everyone that has been a part of this, our partners and those that have provided funding. And I will look at the chat and see what I need to answer, and we'll answer questions later as well.
All right, I'm going to use the laser pointer. It's very exciting for me. So thank you, Allison, thank you for the invitation. I very much appreciate being here today and talking with this really smart group of people, and very much appreciate the organizers putting up with my large absence from the conversation. It's been a busy couple months. It is unfortunately our budget season in Albany the final few days, so I've been pretty absorbed with that the past couple days. But so when you guys stand on the shores of Lake Champlain with your backs to your home state, that's us over there, those mountains you see. This is the Ausable River watershed. It is 512 square miles. As you can get a sense of from this graphic, it's very much, it comes out of Mount Marcy, both the east branch of Ausable River and the west branch of Ausable River. A lot of familiar landmarks there. I think one of the things I, discussed with the group is, we're lucky in that, over 100 years ago, through the 1930s, a series of constitutional amendments in the state of New York created the Adirondack Park, which has protected, given additional protections, especially in these headwater areas. So a lot of our first and second order streams, by their very nature, are in protected areas. That does not mean they have been unscathed. This entire watershed was heavily logged. We'll touch on that a little later. We work in the entire watershed. We also work in some of our neighboring watersheds doing water quality monitoring work, salt reduction work, biological diversity work that very much ties in with our stream restoration work. That's been an odyssey. I'm going to try to run through that for you today. Just briefly, if I learn how to move forward. So if you haven't been to the Ausable watershed, I'm going to let you look at some of the pretty views. And this is the West Branch. It gives you a sense of how confined these valleys are. Yes, that's a road in the right side of the picture, but there is a nice floodplain there on bank right, actually, bank left, I'm sorry. This is on the East Branch of Ausable River. This is actually a pretty nice little section of river that unfortunately the photo down further would show you some nice wood that's planted itself in with amongst these boulders. And, you know, we have nice shading in a lot of our areas. So that's, you know, that looks fairly pretty, fairly functional. This is also on the East Branch in the Hulls Falls areas. We have several natural grade control bedrock systems. It's really a lovely area. But as we all know, I think beauty can be deceptive. What's pretty for the folks that are driving in from New York City and New Jersey, for river restoration folks and people that are used to watching the river might see that underneath that beauty there are issues. And those issues extend to very far back. And yes, that is an English model Ford. I believe it's a Model A. But this is the West Branch, and right away, this is one of our classic iconic areas outside of Lake Placid. So it's, you know, it's the 1900s, and we've got roads already hugging the river. And that's a persistent problem throughout the Ausable. I mean, once again, we're in a protected area. We're not worrying about industry. There's not a lot of agriculture, especially in the East Branch, West Branch sections. We also have a legacy of wood, starting lumbering, starting in the 1800s, very early 1800s. This area was largely settled after the War of 1812 through a series of land grants. That's Nunmark. First, everything was shorn for the iron ore industry, which was huge. It was a national source for iron ore, which required charcoal for burning. 1,000 acres per mill per week at one point, and there were mills just up and down these branches. This is a saw log photo. So we went from iron ore to lumber, to timber, to saw logs, to lumber, to paper. So quite a legacy of industrial use. Also gravel mining was a big detractor. This is on the East Branch, and already, so, you know, it's the early 1900s, we're seeing these massive pieces of erosion. Once again, those stripped banks. This is an interesting structure that you might want to remember for a slide later. That's actually a device that's used as part of a dam structure for releasing waters in spring floods, holding waters, releasing water. So a river that worked very much until 1923, when logging stopped on the system. And that's when the USGS put up our gauges in 1924. Advance, please. Oh, we skipped over. But here's the question that, you know, we often get. It's still beautiful. There's this history, but, you know, we can fish it. So it's all good, right? And not so much. So this is a beautiful picture taken from a drone of the West Branch of Ausable River that just shows you that there's nothing between the river and the road. There's barely any bench there. It's a photo that we actually took for our salt reduction campaign, but you can imagine as the state is maintaining this roadway, they're using salt. New York State is one of the highest salt use per lane mile states in the country. So the proximity of roads is a true issue throughout the watershed, and it creates problems like this in Irene. And Irene was, you know, a high flow. Let's see, a bankful flow in the East Branch of Ausable is 6,000 to 6,500 CFS. Irene was pushing the thermometer at 40,000 CFS. So there was a lot of water moving. This is actually a tributary called Stiles Brook that blew out its side road. Even in the winter, the proximity of roads has another lovely problem. Ice jams are famous here. We had one just a month ago that turned out to be the second highest floods in the history of gauging on the East Branch of Ausable River, coming in just behind Hurricane Irene, but it acted as a seiche. It was a wave that came through the community. We also deal with aging infrastructure. Some of it we have gotten to take down. This used to be the J&J Rogers Pulp and Paper Mill Dam, later called the Rome Dam, a dam that was built in the late 1800s and built as an OG dam in the 1930s. We removed it in 2018. There's that submerged wood structure. and you can actually find the chains that would drag across it. There were 5 structures in this retaining pool, the backwater pond behind the dam. And it was fascinating when we drained those, we realized that they had cut hemlock right off the very high cliffs. This is in a deep gorge, dropped them in, built these structures, and they were completely intact until, of course, we moved them out of the water. And then there's the fact that we, not only is there aging infrastructure, but, we have these tactics for trying to protect the aging infrastructure. And, we all know that there are implications down the road. None of this is new news for most of you. You've seen a lot of this, but these are the issues that we face. The pressure of development is probably secondary. It's really the legacy of the logging industry and the gravel mining industry, which was active until the 1970s, until the creation of the Adirondack Park Agency. Our non-native invasive plant species that create monocultures are contributors to what is, the predominant problem in sediment terms. It is the Ausable, it is the river of sand. As you can see, our banks are friable. Erosion is very much a natural part of this system, but it has been a real issue and become much more exacerbated over recent decades. To the extent that we're still recovering from the logging industry versus what we've seen starting in the late 1990s and anecdotal evidence of shifts in climate change and storm frequency that are changing our sediment movement and sediment availability in our headwaters area. The opposite side of erosion and sedimentation is aggradation. This is actually the main channel of the main stem of the Ausable River. This is Palmer Brook running into it here, which is a very nice little brook trout stream, actually, that we've done some culvert work on. But this is, this kind of aggradation, forcing water over to one side, threatening a road, threatening a community. These are our primary issues. So just as background, so with all of that and more, because I'm moving so quickly, we've been working since the 2000s, trying to figure out how to get restoration right in this system. There's probably no one way to restore streams. There are many tools and many toolboxes, and the folks that have preceded me have talked, I think, passionately about some of those many tools. They used wisely. With a heck of a lot of science and careful surveying, can benefit our streams, protect water quality, restore habitat, and ensure self-sustaining resilience. And that's certainly something that we're after. Briefly, our stream restoration efforts began in the 2000s. We work very closely with United States Fish and Wildlife Services Cortland office, the Partners in Fish and Wildlife Program. In 2010, together, we built the first tow wood structure that I'll be talking a lot today in the Adirondack Park as a demonstration project for our communities and for our 2 primary permitting agencies, the Adirondack Park Agency and the New York State DEC. So our focus, knowing that there are a lot of tools, having learned some methods, exposed to other methods, over more than a decade, we focus today to the extent we can on a science and context-based integrated process. And I'm not going to spend too much time on this, but just to give you a brief overview and reverberating many of the things that have been said in earlier talks here, our principles are self-sustaining streams. And that means a stream capable of managing flows and transporting sediment in the face of a changing climate while retaining their form, whatever that form may be, in dynamic form. We're very focused on moving beyond repairing symptoms to identifying causes. So, the eroding bank being the symptom, looking past that to understand why it's eroding. We're interested in all the levels of connectivity that we can identify. So we talk about 5 levels of connectivity, the 4 you know of: longitudinal, lateral, that vertical, and then temporal, but there's also a cultural connectivity. We're really interested in connecting people to understanding that, yes, this is what a tiny little stream could look like and should look like here. There's a lot of wood in it. It's steps, it's messy, it has little islands, it has little channels, it shifts, it changes. This is actually the upstream portion of Otis Brook before the first road crossing, where we did one of our first climate ready culverts about 7 years ago now. So our process, I'll give you 2 citations on my next slide, follows Harmon and Starr's, generally follows Harmon and Starr's functional framework. You know, we work to identify project goals with the community. Those are often pretty straightforward, and they often include multiple levels. So there'll be a community resilience goal, there'll be a biological goal and a water quality goal, and there's certainly it's a sort of a geomorphic and hydraulics goal. We assess the full watershed, and it might be a sub-watershed is the full watershed. Full is a relative term. And we're surveying and assessing stream function at the reach scale. So that's an effort to establish existing conditions at each functional level. We're looking for stresses, strengths, constraints, and the future evolution of the channel in the target reach. Sometimes we could understand the past evolution as well. We have a lot of imagery from this area back into the late 1800s. We want to establish the restoration potential, determine the level of restoration that can be achieved. We set design objectives, you know, once again, taking into account those project goals, those assessment results, the constraints and restoration potential. We determine a design approach, you know, and we're looking for, once again, that design approach that can adjust the stream functions to meet project goals and restoration potential. And then we develop the selected design, creating a design that follows the approaches and is self-reinforcing. We build something, we want the river to take it over. We want the river to use it as a tool for moving itself forward. So it's a step forward for a river, not a solution. And finally, it's really important from the very beginning, we establish monitoring plans. Just like the others have spoken, we're engaged in the projects for a period of up to 10 years. We've certainly been working year after year with riparian restoration methods. And just super briefly, these are the, you know, I've given you the citations here, and I can send them out to others, but most of you probably are familiar with the stream evolution triangle, which I think is a really nice sort of mixed way to talk about some of the same concepts that come through in the stream function pyramid. There are many models like this that sort of help people think about the interrelationship of these processes and the trade-offs within them. And that does sort of affect how you're going to do your work. So I'm going to talk about one slice of the puzzle. So one tool in one toolbox that we've used, especially productive and enormous opportunity, we think, for restoration, riparian restoration potential and lateral connectivity potential. It's called toe wood. Yes, banks of streams have toes. No, they don't look like your toes, but they're basically in the same spot. We also have a variant that we've been calling root wrap, and that doesn't mean I'm going to sing. This is a pretty picture of a toe wood. Yes, so we're working on streams that are rivers. You know, they're 180 to down to maybe 65 bankful. We don't tend to work on our wild streams. We work where infrastructure comes into conflict with rivers, and we try to place the river first. There are many voices for the infrastructure. We often argue for moving infrastructure, whether that's managed retreat or trying to get a road moved, but in many cases, economics speaks loudly, and we end up doing the kind of work that we've done here. This is a toe wood bench. We're gonna look a lot more at it. This is the start of a project that ended up, there's a very famous fishing pool here called the Culvert Pool. There was another toe wood bench built in here, a lot of collapse going on in these trees here. And then we built out this inner area to sort of get the stream power back to move material. In a bankful event, 1-ton stone moves pretty easily in these systems. So we have to start with thinking about how we use that power to the stream's advantage. This is that same area. This is actually the toewood here that has grasses on it about 2 years after it was originally built. This is called a converging rock cluster. It's a way of setting grade, oxygenating water. There's a J-hook down here. We use these tools out of the toolbox in order to recreate these systems, but we're going to focus on the toewood. Just quickly, you know, toewood, this is a typical toewood diagram. They were created to reinforce outside bends in particular. They are very stable. So they are in their beginning decades, they probably last 50 to 75 years. Nobody's been around to, you know, wait to monitor to see when they decline, but they do begin to erode and become the bank itself, and you begin to see that kind of movement after 15 or 20 years. Our oldest one is just over 10 years now. But it's basically, we use native trees, usually pulled from within a few miles. We do have lots of trees here. They're 18 to 24 inches in girth. DBH, we use layers of alluvium pulled straight from the stream to build these layers. We don't use sod. It says sod in this one. It's a diagram from out west. We don't even have sod. We only have sand. So that's the basic structure. It's not a pretty process when you're in a big stream, thus the muddy water. There's a machine right here, big yellow machine. But here are those root wad logs. They're at a very specific angle, pointing upstream, sitting on top of footer logs. Then we use the whole tree when we pull the tree. So then the slash from the upper part of the trees is laid on top. We take coir fabric, which does break down over a period of years. We lay it on the ends. We fill it with alluvium. We pull it over. We repeat. In this case, we built 2 layers to get to design height to create what is here a bankful bench. Bankful would be back here. So basically, this is going to be absorbing water. We'll see this project, which isn't the prettiest project, but we'll see an overhead picture of it. But that's the basic construction. And then we put a light layer of alluvium on top. We can't put topsoil or anything on top because, you know, it's August and September we're building. We know that water's going to be coming up on these things. We do seed and plant them immediately, seeding immediately. This is actually a year after. So this is the next spring. You can see our seed has come up. In this case, we had transplanted alders on the end of the banks. Beavers love toewood. We'll show you some pictures, and they love these handy alders we put here. And then we're starting our planting process, which I'll just touch on briefly. Hang on. Yeah, okay, sorry. So as I said, toewood is used for outside, and here's just a quick example of where it's come in handy. So this is a bend above a water main that was exposed by what we call the Halloween storm. The town of Keene asked us to come in and find a natural solution, a softer solution, instead of rip-wrapping or re-engineering. We worked with the U.S. Fish and Wildlife Service to develop a design. This is Cascade Brook that comes in here. This house is precipitously close to a high bank that you'll see. But this is a typical good spot for a toewood structure if indeed it's addressing the cause, and it's, you know, it's part of a larger plan. We don't just find nice banks and throw toewood structures on them. Once again, here's the basic construction. If you look at this house, there's that house with that bank. This happened in Irene. What's interesting here is here's Bankful. This is the river rearmoring itself, trying to get this work done of rebuilding its own bank, giving itself wood, which we did incorporate, by the way, when we built this toewood structure. So we don't try to mend these eroding banks because once again, erosion is natural, but we have built underneath it something to slough onto to recreate a more natural bank, big yellow machine. We keep them out of the water as much as possible, but we sit in the water too. Once again, outside bend, deep pool. So quickly, root wrap, which we probably should just call toewood, but we like saying root wrap. This is a smaller project. I think bankful width here was 35, 40 feet. This is a Irene event. Normally, you know, this is this is Rocky Branch right before it meets its confluence with the East Branch. And normally we would go, yay, we're going to create a delta. Nope. Unfortunately, it's good to know your history in these parts. This used to be the site of a brick making factory. So underneath about 2 feet of layer of sod is all the ash. And we didn't want that to mobilize in the system. So in this case, we worked with DEC and APA, and we decided, we made a decision to move the system back to the channel that it had been residing in for some time. But we wanted to do that in a way that was effective. How do I do this? Ah, there. So this is the first time that, Carrie Ann Persian, who developed our biodiverse habitats program, was thinking about this probably a long time, but we'd also been thinking about, how quickly can we revegetate this? What do we revegetate with? How can we figure out what's really sturdy in these toewood scenarios? It's alluvium dependent. You can see the large trees in there. This is a variant of toewood, once again called root wrap. But this was a very successful project that continues to be a monitoring site for us. And it made us think that we can start using toewood in other situations. This is a project we did last year. It's part of the East Branch Restoration Plan, which was funded by the Governor's Office of Storm Recovery in response to Irene. It is one of 13 projects. We did this with a very new firm in terms of the implementation, and it was a learning process for them. We normally like to make, I'm saying this as a caveat, we normally like to make our structures, our rock structures, as natural as possible, but this was a less successful project in that sense, though everything's quite functional. We're very happy with it. So this is, this is an area that's, as you can see, it's right now, I think that's 260 feet wide, that channel, and it's supposed to be roughly 120 to 130 bankful width. Fully intact channel down here. It's absolutely gorgeous down here. But it's a graded central bar. This channel that goes off to the left has been growing wider and wider. It is not a natural channel. It was a channel that was created for gravel mining in the 20s and 30s. This is a complex area over here that we wanted to create ecological uplift, so we created a vernal pool system there. And just FYI, you can see there's more erosion taking place. That toewood demonstration that I walked you through, those 5 slides, that took place right in here. There's that channel. This is the main channel. So here's like 2 days after the project end. These are W weirs that you can see here. They have converging rock clusters after them. This will all be shaken out. I can't wait to see this shot from the drone this year. The ice that came through, the floods that have come through, I think are going to really have sort of messed this up a little in a way that is exciting to us. This channel worked in our ice jam that broke really effectively. We had ice move all the way through it. This is at bank full, and so it moves through as a stopgap, taking on additional water, but it also is feeding those vernal pool systems down there. These benches just eat up sediment. They move sediment out of the system. They move ice out of the system. We've got much more capacity here for moving our large cobble and material efficiently downstream. And it's a lot narrower. So now we're at a nice bankable height there. So this is the Dream Mile towwood, the first that I showed you. I think I took this photo in 2020. It's been an enormous success for us, and it is a study site for our biodiverse habitats program. It's provided us a unique challenge. How do you grow on top of alluvium? Well, it starts with seeding, and you would depend on volunteers, but in the end, it's the river that, if we do our job correctly, the river brings us the sediment, deposits it on our towwood benches, and starts creating that rich medium for those grasses to begin to flourish. We've been very focused on long-term testing and monitoring of riparian success. We started with the U.S. Fish and Wildlife Service Vermont office's riparian planting plan and plants. We've drilled down over the past 5 years, thanks to Lake Champlain Basin Program funding, to figure out what our hyperlocal species are by going up into our upland areas and really doing some careful plant research. We have our own Ausable upland mix now. We're working with a set number of plants that we know are very resilient in ice and flooding, and love to grow in these areas. We're pretty excited about that. So the final message after rushing through this is that wood is good. As soon as we put wood in here, much like as soon as we put in a climate ready culvert where there's a blocked perch culvert, we have fish, we have critters. Again, the beaver love these as well. And they're one way of adding wood on a large system. That's a first step. I would love to get my chainsaw out and start dropping some of these trees and putting them in proper place. But first, I think we need to get our sediment transport, our competence and capacity down in this system. And so that's where we're working. There's the fish that come to our towwood. They're pretty happy there. And so it's been a very successful process for us. We continue to learn, and I look forward to looking through the chat questions.